in the case of functional model. Okay, but sequential model and functional model, these are two important models included in Keras. Then after defining what model we have to use, next is we have to add different layers one by one, and for that again we have a dedicated functionality, and that functionality is known as add. So model DNN-SUQ dot add Keras dot layers dot flatten input shape, that is 28,28, and actually this represents the input layer of that deep neural network. And here flatten input shape is equal to 28,28. In our training data set, all the images are of size 28 by 28, right? But I'm going to create a deep neural network, and in a deep neural network, the input layer actually always expect a one-dimensional array of values, and for that we have to convert our image as a one-dimensional array, and this one-dimensional array now contains various pixel intensity values, and now after that normalizing operation, all the intensity values now mapped onto values lies in between 0 and 1. Okay, so and here that image of size 28 by 28, that is a two-dimensional array initially, and that two-dimensional array is converted into a one-dimensional array with the help of the functionality, and that is flattened. So this statement actually defines the input layer for the DNN model. Then now we can move on to the next statement. The next statement is model DNN-SUQ dot add Keras dot layers dot dense with parameters 300, activation is equal to RELU, and this defines the first hidden layer. And what is the information contained in that layer? And that definition actually contains some parameters, and the first parameter is 300, and that actually represents the number of neurons contained in that particular layer. And this is actually number of neurons, that is actually a hyperparameter, and in a deep neural network or in a conventional neural network, there are two different types of parameters, trainable parameters and hyperparameters. Trainable parameters means all the weight values, weight values contained in the different in between various layers of the network. All these weight values are trainable parameters, and here this parameter can be considered as a hyperparameter, and it is the responsibility of the user to fix the number of neurons. So this can be considered as a hyperparameter. So in the first hidden layer, as per this particular definition, how many neurons are included? 300 neurons. Then again, when we move on to the architecture of that perceptron model, in a single perceptron, a summation operator is there, and the output of that summation operator is passed to the activation function. So activation function is very important in each neuron, and here 300 neurons, and in each neuron we can use a very efficient activation function. That is a nonlinear activation function, and that activation function is known as RELU, and that activation function can be specified here. And here we can use any activation function, sigmoid activation function we can use, softmax activation function we can use, Spanx activation function we can use, RELU, then leaky RELU, etc., etc. Number of different activation functions are there. And in this particular implementation, I am going to use a very efficient activation function, and that is known as RELU. But this defines the first hidden layer. Then the next statement that defines the second hidden layer. The only change in that particular hidden layer, I included only 100 neurons with the same activation function RELU. So two different hidden layers are defined. This is the first hidden layer, and that hidden layer contains 300 neurons. Second hidden layer that contains 100 neurons. And in all these hidden layers, the activation functions. But here, 300 neurons, in all the 300 neurons, we use the same activation function, that is RELU. Then the next statement that is very important. This is the output layer, and this is also a dense layer. This is also a dense layer, but that contains only 10 neurons. Why this 10 neurons? And because this is a 10 class problem. This is a 10 class problem, and in that output layer, the activation function used is softmax. So as a result of including this softmax activation function, when we input a particular image into this particular model, this model outputs 10 probability values, because 10 different neurons are there. Then because of the introduction of this softmax function, as an output of these 10 neurons, 10 different probability values are generated there, and based on the probability values we can take the decision regarding whether the image contains a shirt, whether the image represents a trouser, etc., etc. And then, since the model is a sequential model, the connection between the input layer and the hidden layer, then from the connection between this hidden layer and this hidden layer, and the connection between this hidden layer and the output layer, and these connections are automatically implemented there because of the model selected that is sequential. So this is the model used for building a deep neural network for classifying the images included in the part of as a part of the fashion MNIST dataset. Okay, and again, it is your responsibility. You can add one more hidden layer. You can directly add. For that, we can use the same statement. This add statement can be cut and paste in between the output layer and this hidden layer. For example, dense. Suppose I have to use another hidden layer having 50 neurons, and for that here you can add model DNN seq dot add keras dot layers dot dense with 50 comma activation is equal to RELU. So in that case, the model becomes a complex, a more complex model is generated there compared to this model, because in that model 3 different hidden layers are there. About how many hidden layers, how many neurons in each hidden layer, and all these things are decided by the users. So number of hidden layers, number of neurons in each hidden layer, and all these are hyperparameters of the model. And when we use this particular statement, model DNN seq dot summary, it will print an information like this, and in that information we can see the total number of parameters, that is total number of trainable parameters, and 2,66,610 trainable parameters we can expect in that particular model. And why these parameters? Huge number of parameters. That means, and here in between the hidden layer and the first in between the input layer and the first hidden layer, we can expect one matrix of weight values. Okay, because all the inputs are connected to the 300 neurons. All the inputs are connected to the 300 neurons. In each connection, we can expect one weight value. Okay, so here all these weight values are represented as a data structure, and that data structure is nothing but a matrix. Okay, 2-dimensional array. Then in between the first hidden layer and second hidden layer, again we can expect some weight values. Similarly, in between the hidden layer and the output layer, again we can expect a number of weight values, and all these weight values are stored as matrices. So in all these matrices, how many weight values? 2,66,610 weight values we have to expect in that particular model, and that is the information corresponding to the model summary. Okay. Then once the model is built, the next task is to convert that model suitable for training the data set. That means to extract the knowledge available or contained in that particular data set. And for that, as a first step of the process, we have to compile that model first. So model DNN seq dot compile. And that is, in order to compile that model, we have a dedicated functionality, and that dedicated functionality is nothing but dot compile. And inside that compile method, a number of parameters we have to specify. The first parameter is the name of the loss function, and here the loss function is sparse categorical cross entropy, because this sparse categorical cross entropy is included in this model as a loss function because of the reason that and here this is a multi-class problem. 10 different classes are there. Okay, and if it is a two-class problem, instead of this sparse categorical cross entropy, we can directly move on to binary categorical binary cross entropy. Binary cross entropy, that is another loss function. A number of different loss functions are there. In this particular model, I just use sparse categorical cross entropy because my problem is a multi-class problem. Then and in order to implement the gradient descent approach, as a next parameter, we have to provide an optimizer function. An optimizer function, it is the responsibility of the optimizer function to tune the weights. Tune the weights between the input layer and the first hidden layer, then between the first hidden layer and second hidden layer, etc., etc., and between the output layer and the just above the just hidden layer, just before that particular output layer. Okay, but that type of an optimization is there, and this optimization or weight tuning is actually done with the help of an optimizer function. And here I'm used an optimizer function Adam. A number of other optimization functions are also there. Stochastic gradient descent, then RMS prop, etc., etc. A number of different optimization functions are there. And while choosing the loss function and optimizer function, we have to study about the properties of the data set and what type of values are there in the data set, and what type of problems we are going to solve. And according to, or by studying all these things only, we can fix the loss functions and the optimizer functions. Then in order to evaluate the performance of the model, we need a metric, and in this particular example I'm going to use the metric accuracy. Some other metrics are also there, like loss, etc., etc. Loss can also be a fun score, then a number of other ROC area, and a number of other matrices are there. And but in this particular example, I am going to use the metric known as accuracy. And for the time being, we can just forget about this particular statement because I am going to discuss, not going to discuss the information behind this particular statement, because we are actually using a TensorFlow environment in this particular implementation, and that is a graph-like structure. And what is the information flow in which path, and that type of a graphic structure we can create with the help of this particular statement. And for the time being, we can just forget about this particular statement. Then this is the next, that is after building the model, the next task is to compile that model, and compilation can be done. And again, you have to understand what type of an activity is going to happen at the time of executing this particular statement, that is compile statement. That means in that model, a number of different matrices are there, and all these matrices are initialized, and it is the responsibility of this compile method to initialize various matrices available in between the various layers of that particular model. Okay, then we have to compute the loss. Okay, compute the loss means by comparing the actual output and the predicted output, and that actual output and predicted output, by considering these two parameters, the loss values, and that is actually computed by the loss function. That is the responsibility of the loss function. Then back propagate that loss, and that is the responsibility of the optimizer function. Then the performance of the model, and that is actually evaluated with the help of this metric. Then after the compilation, the next task is to train the model. That is, after building, compiling, the next task, that is to train the model. And in order to train that model, we have a dedicated function, and that method is known as fit. So model DNN SUQ dot fit with parameters, that is, in order to train, we have to provide the training data sets. So the training data set is nothing but x train comma y train. Then next parameter is in how many times we have to train that model. And in this particular example, I just used epochs is equal to 10. So 10 different iterations we can expect there. Then validation split is equal to 0.1. Validation split is equal to 0.1. I think in your first introductory machine learning class, I think Dr. Judy discussed about the k-fold cross validation. Okay, but here, what is the use of this k-fold cross validation or validation split? But here, in order to eliminate some data set, actually have some problems with the values contained in that data set. So the output generated by the model with the help of that data may not be accurate. So each time we have to evaluate. If we have to evaluate whether the model, the result created by that model is accurate, whether the model the value created by that model is accurate, etc., etc. And that validation is actually done with the help of a validation split obtained from the training data. So, and from the training data, in this case, 10% of the images are used for validation at each epoch. At each epoch, we validate the data or validate the result obtained from that particular model. And for that, with the help of this k-fold cross validation, we can eliminate a limitation associated with models like DNN or CNN, and that limitation is nothing but the overfitting. Again, I don't like to discuss more about this overfitting. Overfitting is nothing but during the training we get a very good accuracy, but when we use the model for testing, the model will fail, and that properties actually is known as overfitting. And with the help of this validation, we can solve the problem of overfitting. So from among the training data set, 10% in this particular example, 10% of the data is reserved for validating the information obtained from that particular model. Okay, so history SEQ, and this is an object. Model DNN SEQ dot fit x train y train, then epochs is equal to 10, and validation split is equal to 0.1, and this parameter is not needed because we don't want to discuss this particular statement. If this particular statement is included, this statement is very important. Okay, and for the time being, you just consider the parameters up to the validation split, that is 0.1. Then when this particular statement is executed, inside this history SEQ that can be considered as a one-dimensional array, and inside that one-dimensional array, we can expect a number of different information associated with that particular model corresponding to each epoch. And history SEQ now contains the training accuracy, and in that particular epoch, what is the training accuracy obtained, then in that particular epoch, and what is the validation accuracy obtained, training loss, then validation loss. These type of informations are automatically stored in this particular object, that is history SEQ. Okay, that is so after building the model, we have to train the model as a in order before training or before convert that model for training. As a first step of the model, first step of the activity, we have to compile that model. Then after that, we can train the model with the help of fit. Then when we train that model, this type of progress we can see at the time of executing that particular model. And when we consider the information corresponding to the first epoch, that is 10 epochs are there, and this is the information related to the first epoch. Now the loss, that is at the time of training the data. This is the loss obtained there, and this is the accuracy, that is the training accuracy, and this is the validation loss, and this is the validation accuracy, because all these informations are now available in the history information. Okay, and that is the case with deep neural network, DNA. Okay, I think you are now you are familiar with how we can create a deep neural network, then how we can train that model and so on. Okay, then what are the various parameters, and what is actually the trainable parameters, and what is actually the hyperparameter and so on. And these are some basic concepts related to deep neural network. Then now we can now directly move on to convolutional neural network, because these two constructs, the convolutional neural networks and deep neural networks, are very important for constructing the generative adversarial networks. And very quickly we can move on to the basic concepts of CNN. A detailed overview of what CNN do, and that is actually there is always a slight difference between the DNN and the CNN. And here in CNN, the first step is or CNN takes the input as the image. Image is the input in the case of CNN. Then after that, we can pass this image through a series of convolutional, and that is first layer, then non-linear, that is RELU, then downsampling, then fully connect layers and get an output. So in a convolutional neural network, the image passes through different stages. The first stage is known as the convolutional layer. Then after that, it passes through the non-linear layer, that is the rectified linear unit. A separate unit is there. It passes through rectified linear unit. Then it passes through another very important layer, which is known as the pooling layer, or the pooling layer is also known as downsampling layer. Then after passing through the downsampling layer, we get some important features corresponding to that particular image, and these features are now passed on to the fully connected layer. And this fully connected layer is nothing but a deep neural network. And in that neural network, as a last step of the process, we get the corresponding output, and the output is nothing but a probability value. The output can be a single class or a probability of classes that best describes the image. And single class means if the problem is a two-class problem, we get a single value. Based on that value, we can take the decision regarding whether the image contains a car or not, for example. Or a probability of classes. In the case of a multi-class problem, we get a number of probability values. Based on those probability values, we can take the decision. Okay, and that probability value describes the decision, or they describe the image. Then this convolutional layer, and that is very important. The convolutional layer is the core building block of a convolutional neural network, and the input to this layer is an image. Input to this image is this layer is an image, that is a 224 by 224 by 3 array of pixel values. For example, in our previous problem, 28 by 28. Okay, but in this case, for example, the input image is 224 by 224. That is the size of the image, and this 3 represents the image. Image is a color image. That is, in a color image, we can expect 3 different channels, RGB channels. 224 by 224 by 3 array of pixel values. And the convolutional layer's parameters consists of a set of learnable filters, because this convolutional layer actually contains a number of parameters. And the first parameter is the filters. How many filters are there? And the filter, and what is the concept of a filter? And the filter is a small array of numbers, and these numbers are actually known as weights or parameters. And parameters means the learnable parameters. And in the case of a perceptron model, each input is associated with a particular weight value, right? But here, each filter and the weight values are actually stored in a particular data structure, and that data structure is actually known as a filter. A filter can be considered as a two-dimensional array, a small two-dimensional array compared to the input image. For example, a typical filter on the first layer of a convolutional neural network might have a size of 5 by 5 by 3. Okay, this is a filter, and the depth of the image and the depth of the filter, this is always same. But here in that filter, how many weight values we have to expect? How many weight values we have to expect? 75 weight values we have to expect. That is 25 into 5, that is 25 into 3, that is 75. Okay. And in the it is the responsibility of the training algorithm to tune these weights. That we will discuss later. The first position, we place the filter in the top left corner of the image. First, we place the filter is the top left corner of the input image. And the filter, the region covered by that particular filter in that image, and that region can be considered as a receptive field. That region is actually known as a receptive field. Then the values, the operation actually happening there is nothing but then the values in the filter is multiplied with the original pixel values of the image. That is computing element-wise multiplications, as in the case of the single perceptron model, that is W1x1 plus W2x2 plus W3x3 plus etc. In this case, all the weight values are contained in the filter, and the receptive field is there. And in the receptive field, we always expect the pixel intensity values, and these pixel intensity values are actually known as x values. So W1x1 plus W2x2, and these type of multiplications and summation, that is element-wise multiplications are happening there, and after that these multiplications are all summed up, and the result is you can imagine the result is a single number. Then what is the importance of this single number? This number gives the presence of the feature representing the filter in that image, input image. That means this filter actually represents a particular feature of that image. Okay, whether that particular feature is available in that receptive field or in that particular position, that can be determined with the help of this element-wise multiplication and summation. And that means if this element-wise multiplication and summation returns a very high value, that means the feature contained in that particular filter is available in that particular location. Okay, and that type of an information can be extracted with the help of the convolutional layer, with the help of that filter. So this is the filter, and bottom of that filter we can expect the receptive field. And when we perform the element-wise multiplication and summation, we come up with a numeric value, and this numeric value is now mapped onto a matrix. Then these are some example or visualizations of the filters of the first convolutional layer of a trained network. As I said earlier, in the first convolutional layer or in the first hidden layer, we can extract some basic features of the image. This can be considered as a basic feature. This can be, and that is after the training process. If we display the filters, these type of informations we can visualize. These are some the filters or visualization of some filters used in a convolutional neural network. That is actually the first convolutional layer. We can expect this type of features or filters. And what is actually happening inside the convolution layer? But here we have a 5 by 5 image, and in order to extract the features, we use a filter of size 3 by 3. And when we perform the element-wise multiplication and summation, we get a value, and that value is mapped onto a matrix, and this is the first value. Okay, but here this is the first location, and the corresponding to that particular location we get a value, and that value is 4. And after that we convolve or move one location right to that image. Then as a result we get another value, and that value is mapped onto the first row, second column of the matrix. Then after that again we can move on to the next location. So as a result, we get another value, and that value is mapped onto the first row, third column of the matrix. And in this way, we can fill all the entries of that matrix. And so this matrix is very important, and this matrix is actually known as a feature map. And this feature map will give you the information regarding in what are all locations the feature represented by that filter is available, and that type of a spatial information, and that is available in this feature map, and generating this feature map, and that is the main objective behind the convolutional layer in a CML. Okay, but this is the case with one filter. This is the case with one filter. And instead of that, if you use two different filters, we get two feature maps. Three different filters, we get three feature maps, and so on. So number of filters actually corresponds to the number of feature maps. Okay, then about here in the convolutional layer, we can generate the spatial information regarding the various features contained in the image, and the spatial information is always available in various feature maps. And after that, an additional operation called RELU, and that is the rectified linear unit, has been used after every convolution operation. And RELU stands for rectified linear unit, and is a non-linear operation, and its output is given by output is equal to max of 0, input. That means in the case of a feature map, the number stored in that matrix, actually this number is a reflection of the presence of the feature representing the filter in the corresponding position of the input image, and that I already explained. And if the generated number is large, which indicates the presence of the feature at that region. Okay, then here we always concentrate on large numbers. We always concentrate on large numbers. We don't want any type of negative numbers. So as a first step of that process, we can eliminate all these negative values from the feature map with the help of the RELU operation. And that is the reason why we use the RELU as max of 0, input. So negative pixel intensities or negative informations can be eliminated from that particular feature map. So RELU can be considered as an element-wise operation, replaces all negative pixel values in the feature map by 0. All the negative values can be replaced with the help of the 0 values. And so after the convolution operation, we have to perform the RELU, and this RELU is actually applied in every information contained in the feature map. But here, if we use 3 different filters, we have 3 different feature maps. In all these feature maps, we have to perform the RELU operation. And instead of 3, if we use, for example, 64 feature map, 64 filters, 64 different feature maps we can expect in that particular case. So in all these 64 feature